So what we saw just now, it was valence bond theory. Okay. Now what are the limitations of valence bond theory? Limitations, when you consider, your textbook is giving very clear picture about that. It is involving a lot of assumptions, is it not? So what we told, just because unpaired electrons were there, it was showing magnetic behavior. So from the magnetic behavior, they found that which orbitals are participating in hybridization, which are not participating, the electrons must have got paired. All these assumptions were made, is it not? So it involves a lot of assumption. Then it does not give any quantitative interpretation of magnetic data. It is all based on assumption only. We are able to find out. If the magnetic moment is high, then we assume that there are more unpaired electrons. If the magnetic moment is less, then there are less number of unpaired electrons. Like that we are assuming. Then it does not explain the color exhibited by coordination compounds. And it is also not giving anything about kinetic stability of these compounds. And why certain complexes are tetrahedral, some of them are square planar, some of them are octahedral. Okay, all these exact predictions regarding the geometries, they were not able to explain. And it is also not distinguishing between weak and strong ligands. Now all these drawbacks, they are to some extent cleared when they started with another concept, that is crystal field theory. Now this is giving you an electrostatic model, and this is explaining to some extent whatever drawbacks are there in valence bond theory. You can try to overcome all that. Okay, now this crystal field theory, what is it considering? It is considering the metal ligand bond as purely ionic. Okay, metal ligand bond is purely ionic, and the electrostatic interaction between metal ion and ligands is what it is explaining. And it is also assuming that the ligand is anion and the metal atom is cation. And if the ligand is a neutral molecule, then the negative end of the dipole is attracted towards the metal atom. Say for example, it is ammonia, it is nitrogen which is more electronegative, so that is getting attracted towards a metal atom. If it is water acting as a ligand, then oxygen is getting attracted, like that. And the ligand is considered to be a point charge, a point of negative charge. That is what is considered. Then the arrangement of ligand around the metal ion is in such a way that there is minimum repulsion between them. If there are 6 ligands, in what way they are arranged? It is such that the ligand electron clouds, they do not repel with each other. So that is another condition. So these are the basic things that crystal field theory is considering. Okay. Now, in the case of this crystal field theory, there is again one more assumption, that the d orbital is undergoing splitting. Now this is the set of d orbital. Okay, I have assumed 4 electrons in the d orbital. Now in the presence of strong ligands, it is undergoing one kind of splitting. In the presence of weak ligands, it is undergoing a different kind of splitting. Now, why this splitting should take place? That is because when you consider these d orbitals, they are 5 in number. This you know it. Now these 5 d orbitals, 3 of them, you will find the lobes in between the axis, like in the case of dxy, dyz, the lobes are like this. They are in between the axis. It is like this. Whereas if it is dx square minus y square, there it is like this. It is like this. Now here the lobes are along the axis, whereas in dxy, dyz, dxz, you will find the lobes in between the axis. This is the axis and the lobes are in between the axis. Okay, so two of them, this dx square minus y square and dz square, both of them, they are along the axis. It is like this, dz square and a cloud around it. This is your dz square. This is dx square minus y square. Now dxy, dyz, dxz, they are all of this type. Now when the ligand, when it is bringing a pair of electron, when the orbital is approaching, it will have to overlap. See, that is bonding, is it not? Now that overlap will always take place along the internuclear axis. Now along the axis, this axis पे वो overlapping होगा. तो मान लो वो ligand का जो orbital है तो ऐसे आ रहा है. If it is coming like this, along the axis it is coming. Now the lobes of the metal atom is in between the axis and the ligand orbital is coming along the axis, right? So they will be suffering from less repulsion because ये दूर दूर है. अगर वो dx square minus y square या dz square के ऊपर आता है, उसके ऊपर overlap करता है, then already the metal atom की d orbital lobe भी है, तो ये lone pair of electron जिस orbital को overlap कर रहा है वो भी axis पे आ रहा है. So their metal electrons and the ligand electrons के बीच में आपस में repulsion होने की chances ज़्यादा है. उसकी वजह से इन्होंने क्या बोला, अगर a set of 5d orbitals है, these 5d orbitals, they are splitting into two. They assumed a set of 3, that is these 3, in which the repulsions are less, so they are associated with low energy, and a set of 2 on which the overlap is taking place along the axis. So metal d orbital and the ligand orbital, they may undergo repulsive forces, so they will be at a higher energy. So this is called as T2G, and a set of 2, this is called as EG. So this is what you call it as d orbital splitting. Okay. Now when this splitting is taking place, the degeneracy of the d orbitals is lost. You consider that all the d orbitals are degenerate. Degenerate means orbitals having same energy. Now once the splitting is happening, that means there is no more degeneracy. It is totally removed due to ligand electron and metal electron repulsions in the complex. Due to ligand electrons and metal electrons repulsions. Now this kind of splitting is what is taking place in the case of octahedral complexes. So that is what is given here. This is the set of metal d orbitals. First, it is increasing in energy. It is going to an excited state, and at that point of time it splits into two, a set of 3 and a set of 2. This is what is taking place. Now let me again come to my point. If the ligand is strong, then it is causing large splitting. That is, the energy level difference between T2G and EG has been found to be large. And if it is a weak ligand which is approaching the metal ion, then the splitting has been found to be small. The energy level difference is small. Okay. Now if you assume that this energy level difference, if you assume it to be delta O, for octahedral complexes, you are considering it as delta O, and there is one more energy consideration that you have to consider, that is energy due to pairing. Now there are 4 electrons in the d orbital, मान लो, ठीक है, किसी भी metal ion की configuration 3d4 है. Now these 4 electrons, how they are getting accommodated after splitting? Now these 4 electrons, they can first fill 3 according to the same principle, that is Hund's rule. So first they are getting filled singly and then pairing takes place. So all the 4 electrons, they are accommodated in T2G and EG remains vacant. right? This is in the case of strong ligands. In the case of weak ligand, what happens? 3 electrons, they go to T2G, and the 4th electron, instead of getting paired here itself, it prefers to go to EG. Why it prefers to go to EG? Because this 4th electron, had it been here, it will have to pay the price due to repulsions from the existing electron. So it feels that it's better to climb up and stay in EG comfortably without undergoing repulsions. So the 4th electron, it goes over to EG. But in the case of strong ligands, the 4th electron feels it's better to remain in the paired condition in T2G itself, because jumping to EG will take more energy for me, which I cannot afford. I'll better stay here. So in the presence of strong ligands, all of them will try to remain in T2G. In the presence of weak ligands, after filling 3 electrons, the 4th electron will prefer to go to EG. Okay, so this is what you call it as strong ligands cause large splitting. That is why electrons prefer to remain in the lower energy level, and weak ligands cause small splitting. So the electrons may rise to the higher level. Now one more thing what you have to realize here, there will be more number of unpaired electrons here, paired electrons here if the ligands are stronger, but if the ligands are weaker, then you will find more and more of unpaired electrons. Okay, so weak ligands cause small splitting. Why small splitting? Because delta O, that is the energy level difference between the two, is less than that of energy due to pairing. So it prefers to go there, and this is resulting in more number of unpaired electrons. So you try to understand that such a complex will be a high spin complex, because unpaired electrons are there, उसकी spin तो होगी, तो वो high spin complex बनाते हैं. अगर strong ligands होते हैं, in that case, this is very large. So delta O is larger than P. Energy due to pairing is much lesser than climbing over to EG. So electrons get paired up in T2G itself. So less number of unpaired electrons होंगे. So such complexes will result in, such compounds will be low spin complexes. Right? So this is what is crystal field theory all about. Now in the case of crystal field theory also, there are certain limitations, because the ligands are considered as point charges. The anionic ligands should exert greater splitting effect. Stronger ligands में large splitting हुआ था. However, the anionic ligands, they are present at the low end of the spectrochemical series. There is a spectrochemical series by which you are able to assume the strength of the ligands. This is your spectrochemical series. Here you find I minus, Br minus, Cl minus all in the beginning itself. Okay, and towards the end you find ammonia, ethylene diamine, Cn minus, carbon monoxide. These are all coming towards the extreme other end, where you find these are all considered to be stronger ligands and these are all considered to be weaker ligands, in spite of the fact they are halides, which you consider them as the most electronegative in the periodic table. Okay, so this assumption is this particular concept is violating the actual behavior. And it treats the metal ligand bond as purely ionic, and it does not take into account the covalent character of the bond. What is actually happening? It is donation cum sharing, is it not? That means it is coordinate covalent bond. But the CFT is assuming that it is purely ionic. So this is again another limitation of CFT. But otherwise, the CFT is successful in explaining the color, magnetic properties, then effect of strong and weak ligands, then the geometry of the complexes. All such things are well explained by CFT. Now, what are the main factors which affect the crystal field splitting energy, if you ask? Then that is charge on the metal ion and strength of the field produced by the ligand. These are the main two conditions or factors which affect the crystal field splitting energy, right?